The universe has this baby picture. From its very first moments, it's called the cosmic microwave background, a snapshot from when the cosmos was 380,000 years old. Our best theories say this first light should show a calm glow, a nearly perfect one, the quiet aftermath of the Big Bang, but it doesn't. Across this cosmic canvas, there are strange features. Impossible ones, flaws in the fabric of reality itself. These aren't minor imperfections, they're profound anomalies. They challenge the very laws we use to explain existence. The universe might have a preferred direction, a north and south it shouldn't possess. There's a vast, freezing cold patch in the sky. It could be evidence of a collision with another reality. The oldest light in creation is whispering secrets, secrets that defy explanation. That baby picture wasn't always understood. To see why its flaws are so unsettling, you have to go back to the very beginning, when the universe wasn't transparent. It was this searing, churning fog, a dense plasma of fundamental particles, and light was trapped inside it. Photons couldn't travel in a straight line. They'd immediately hit a free electron and scatter. It was a cosmic prison of brilliance, a blinding opacity. That lasted for nearly 400,000 years. Then something shifted. The universe kept expanding and it finally cooled enough. Electrons slowed down. They were captured by protons. They formed the first neutral hydrogen atoms. That moment is called recombination, and it changed everything. The prison bars vanished. With no more free electrons in the way, the photons were set free. They began streaming across the universe in every direction. That first brilliant flash of liberation is what we see. But the universe has stretched since then. Over billions of years, that once visible light has been stretched. Its wavelengths pulled and lengthened by the expansion of space itself. All the way into the microwave part of the spectrum, it's now a faint, cold whisper, just a few degrees above absolute zero, bathing the entire sky. That's the cosmic microwave background. But it's not just ancient light. It's a cosmic treasure map. Imprinted on its glow are tiny variations in temperature, minute ripples, hotter spots and colder spots. These are the seeds of destiny. The slightly denser regions, which show up as slightly colder patches, they had the gravitational potential to pull in more matter. Over eons, those seeds grew. They became the first clouds of gas, then the first stars, then galaxies, the vast clusters of galaxies we see. Every structure traces its lineage back to those specific patterns in that first light. Our leading theory of the cosmos, the Lambda CDM model, makes a profound prediction about this map. It says the patterns should be, on the largest scales, statistically uniform. The universe should have no preferred direction, no grand left or right, no cosmic north or south. The fluctuations should be like a perfectly shuffled deck of cards, showing no hidden order. They should follow what mathematicians call a Gaussian random distribution, a very specific, balanced kind of randomness. This expectation of perfect, featureless symmetry is the bedrock of modern cosmology. The shocking realization, the one that sends tremors through everything, is that the map we have might not match this prediction. The deck appears to be stacked. The universe might be showing us a hand it was never supposed to deal. This first major crack has a name, the axis of evil. It sounds like science fiction, but it's a real feature in our maps of the cosmic microwave background. Our theories say the universe should be isotropic, the same everywhere, no left or right, no north or south. But when they looked at the largest ripples in that ancient light, they saw something impossible, an alignment, a preferred direction. The patterns seem to point to an axis, and this axis, this line through space, it lines up with the plane of our own solar system. It also lines up with the direction our galaxy is moving. It's like drawing a map of the whole world and the continents line up with your street. It suggests our local corner of the cosmos might be written into the oldest light there is. That shouldn't happen. The cosmological principle says we hold no special place. The universe shouldn't care about our solar system's orientation, but the data hints that it might. This large-scale asymmetry is like finding a compass painted on a ceiling in a room with no walls. Some say it's a fluke, a trick of the data, but the signal has persisted. It's shown up in map after map from different telescopes for decades. Its refusal to go away is what's troubling. Could it be a shadow from before the Big Bang? A fingerprint of something that existed before time? Or a sign that cosmic inflation, that early stretching, wasn't perfectly uniform? Maybe it's an artifact. Contamination from our own cosmic backyard, something we haven't cleaned from the lens. But if it's real, it changes everything. It means the universe has a grain, a texture with a direction. And if that's true, then our most basic assumption that the cosmos is smooth and featureless on the largest scales is wrong. We may not be at the center, but we might be looking at a universe that has one. The axis of evil isn't the only thing. There's something else. Far off in the southern sky, there's a place where the ancient light is just too cold. They call it the cold spot. It's this huge, circular region in the cosmic microwave background, and it's much larger and much colder than it ever should be. Like a vast, faint bruise on the sky, a place where the universe's first warmth seems to have drained away. The simplest idea is that it's a cosmic emptiness. A supervoid, an immense region of space, billions of light-years across, where there just aren't many galaxies. When light travels through a void that big, it has to climb out of a gravitational well. That climb takes energy. It stretches the light's wavelength, makes it appear colder. That's the integrated Sachs-Wolf effect. It's a known phenomenon. But the problem is the scale. The cold spot is so profoundly cold. The supervoid you'd need to create it would have to be unimaginably vast, unimaginably empty. A true nothingness. And when astronomers look there, they do find a region with fewer galaxies. But it's not that grand, echoing cathedral of emptiness. It's more like a modestly understocked room. The void we see isn't big enough or empty enough to explain the deep chill we measure. The numbers don't add up. So if it's not a void, what made it? What carved this frozen scar? Some theorists have a breathtaking idea that the cold spot is a collision scar, a remnant from when our infant universe, still inflating, bumped into another bubble of reality. In a multiverse where countless universes bubble up, such a collision could leave an imprint, a cosmic bruise. Others think it could be evidence of a cosmic texture, a defect in the structure of space-time itself, formed during the universe's earliest, most chaotic phase, like a knot frozen into the fabric of reality. These aren't minor adjustments. They're doorways to entirely new physics. The cold spot just stands there, a silent, frozen monument to our ignorance. A reminder that this oldest light we see might be showing us shadows of realms we haven't even named yet. There's this third anomaly. It makes the universe seem lopsided. They call it the hemispherical power asymmetry. The universe appears to have two different faces. When they measure the temperature ripples in the cosmic microwave background, they find an imbalance. One half of the sky, one celestial hemisphere, shows fluctuations that are stronger, more pronounced than the other. It's like the universe's opening act was louder on one side. This isn't just a gentle slope. It's a statistically significant dipole modulation, a fundamental lopsidedness. It has no place in a perfectly isotropic cosmos. According to this ancient light, the universe might be fundamentally uneven. This isn't a subtle effect. It's not a measurement quirk. It's a persistent signal. Scrutinized for years, our standard model of cosmology predicts a sky that is the same in all directions. The power of those primordial seeds should be evenly distributed. Finding one hemisphere more powerful than another is like listening to a symphony and realizing all the violins are on the left. The right side stays muted. It breaks the symmetry, so what could cause it? One possibility is that our universe is not infinite. It might be finite, wrapped in on itself in a strange shape. Think of it as a cosmic hall of mirrors. If space is connected in a certain topology, like a three-dimensional donut, light could travel along multiple paths. It could wrap around the universe and arrive from unexpected directions. This wrapping could create interference, amplifying signals in one part of the sky and suppressing them in another. We'd be seeing echoes of our own cosmos, an illusion of asymmetry from a reality that is still uniform, a universe playing tricks on itself. Another idea points further back in time. This lopsidedness might be a fossil, a remnant from the pre-inflationary universe. The standard story is that inflation ironed out all the wrinkles, erasing any prior irregularities to create a perfectly smooth start. But what if inflation didn't erase everything? What if some grand, primordial irregularity was too big to be smoothed away? This hemispherical asymmetry could be the scar of that initial condition. A relic from the chaotic moment before inflation began. A whisper from a time before time was fully formed. Either possibility forces a confrontation with our theories. If the asymmetry is real, it means the universe's initial conditions were not perfectly uniform. The foundation of our model would have a crack. Inflation theory, in its simplest form, would need a major rewrite. We'd have to accept the cosmos began with a preference, a tilt, an inherent bias written into its first light. This isn't just fixing a calculation, it's about reimagining the birth of everything. The universe's baby picture is flawed. It suggests the infant cosmos was born with two different sides, but the silence can be the loudest clue. There's a fourth kind of anomaly in the cosmic microwave background. A quietness where we expected to hear a chorus. On the largest scales, the universe is whispering when it should be speaking clearly. That's the mystery of the missing large-angle correlations. Think of the ancient sky as a vast network, a web of points, each with a tiny temperature. Our theories predict a certain connection between these points. A correlation. Even points very far apart on the sky, separated by more than 60 degrees, should show a statistical relationship. They should remember each other. Because in the infant universe, before inflation stretched everything, those points were neighbors. They were close enough to interact, to exchange information, to establish a common temperature. That connection should still be imprinted on the light. Yet when we look, that expected correlation on the grandest scales is weaker than it should be. It's faint. Distant parts of the cosmos seem more independent than our models allow. The universe at its largest horizon is quieter than predicted. This isn't about a cold spot or an axis. It's about a fundamental hush in the data, a lack of expected signal, and in science, an absence can be as telling as a presence. What could cause that silence? One idea is it points to a fundamental limit, a cutoff in the primordial fluctuations themselves. The seeds of all structure might not extend to infinitely large sizes. There might be a maximum wavelength to the ripples inflation created. Like a pond that can only support waves up to a certain size, the early universe may have had a natural limit to how large its initial irregularities could be. That isn't predicted by the simplest versions of inflation. It would require something new in that explosive first moment, a feature in the physics of the birth itself that imposed a scale. Another possibility is even more mind-bending. This quietness could be a clue about the shape of all reality. The large-scale correlations we expect are calculated assuming space is infinite and flat. But what if it isn't? What if the entire cosmos is finite but without an edge? A topology where space wraps around on itself, like a three-dimensional version of the surface of a sphere. In such a universe, there's a maximum possible distance between any 2 points. There are no scales larger than the universe itself. That fundamental limit would naturally suppress the very largest correlations we try to measure. The quietness we see could be the echo of our cosmos's own closed geometry, a hint that everything we observe is just one immense, but finite, bubble. This anomaly doesn't shout. It murmurs from the very edge of our observable horizon. It suggests the story of inflation of that initial explosive stretch might be incomplete. Perhaps the universe began not with a perfect, smooth symphony of infinite wavelengths, but with a more nuanced overture, one that had a natural end to its lowest notes. Or perhaps we are seeing the curvature of reality's stage. The quiet at the largest angles is a profound puzzle. It tells us that even in its first moments, the universe may have been obeying rules we have yet to fully hear. But the alignments don't end with just one axis. There's another layer to this, a second, independent pattern that seems to be saying the same thing. You have to look at that ancient light through a different mathematical lens. Scientists break down the temperature map into components. They call them multipoles. It's like listening to a complex piece of music. You can separate the overall sound into distinct notes, into harmonies. The quadrupole and the octopole are two of those fundamental harmonies. The quadrupole describes the simplest, largest deviations from a perfect sphere, a kind of cosmic lopsidedness. The octopole is the next harmonic, a slightly more complex pattern of hot and cold. In our standard model, these two patterns should be completely independent. They should have no reason to line up. They're different notes in the symphony, played by different instruments, but they do align. Their planes of symmetry are oriented in a strikingly similar direction. And this shared orientation, again, points suspiciously close to the plane of our own solar system. That's the Quadrupole-Octopole Alignment. It's a coincidence of cosmic proportions. The chance of these two independent patterns aligning so precisely by random accident is extraordinarily low. The odds are so slim they make statisticians deeply uncomfortable. It's like rolling two dice 1,000,000 times and having them land showing the same two numbers, facing the same exact direction every single time. This isn't just a fluke. It's a signal. This alignment adds tremendous weight to the earlier mystery. It's not one anomaly pointing in a strange direction, it's two, both whispering the same thing. That the largest scale structures in the universe's first light are coordinated. They share a hidden symmetry, a preferred frame of reference that, according to all our foundational principles, should not exist. This coordinated pattern implies the primordial seeds for all structure. The very blueprints for galaxies were not perfectly random quantum fluctuations. They may have contained hidden correlations, a subtle order woven into the chaos of creation. What could impose such an order? One possibility is that the process of inflation, that hyper-stretching of spacetime, was not perfectly uniform in all directions. It might have had a slight directional preference, a gentle cosmic grain, that imprinted itself on these largest patterns. Another idea, even more profound, is that this alignment is a fossil, a remnant of physics from before the Big Bang, a structure or a field that existed in the primordial state and set a preferred direction for the newborn universe. Like a cosmic mold that shaped the first light, this alignment challenges the very notion of a perfectly isotropic and homogeneous beginning. It suggests the infant cosmos may have been born with a subtle twist, a fingerprint on its surface. For cosmologists, it's a haunting clue. The universe's baby picture isn't just flawed. It seems to be winking at us, hinting that the story of our origins is far more intricate and far more strangely connected to our local place than we ever dared to believe. The statistics of that ancient light. There's a sixth anomaly, a subtle one. It comes down to a word, Gaussian. Our theories predict the temperature ripples should follow a Gaussian distribution, a cosmic bell curve. In a perfectly Gaussian sky, the hot and cold spots are arranged in a particular randomness. No hidden patterns, no secret handshakes. The size and distribution of the spots would be fully described by simple statistics. Bland, featureless randomness. That's what the simplest inflation models would produce. Quantum fluctuations stretched across the universe, and for the most part the sky obeys this. It's remarkably Gaussian, almost eerily so, but the key word is almost. When scientists peel back the data layer after layer, hints emerge. Tiny suggestions the statistics might not be perfectly pure. They look at complex relationships. The bispectrum, That's not just measuring individual hotspots. It's searching for subtle correlations between triplets of points on the sky. A faint whisper of a connection a simple bell curve can't explain. It's the difference between random static and catching the faintest rhythm of a distant drum. Finding definitive proof of this, non-Gaussianity, would change everything. It would be a direct fingerprint, a specific signature from the universe's first fraction of a second. If the primordial fluctuations weren't perfectly Gaussian, it means the process that created them, probably inflation, wasn't driven by a single, simple quantum field. It could mean multiple fields interacting, or that the inflattened field itself had a more complex shape, a richer texture, as it rolled down its energy landscape. The specific statistical signature would be like a barcode, telling us exactly which version of inflationary physics was in play. It would move cosmology from broad strokes to fine detail. We wouldn't just know the universe inflated, we would know how. This search is a razor's edge. The instruments are phenomenally sensitive, sifting cosmic signal from noise and the foreground glow of our galaxy. Every claim of a detection is scrutinized, every potential signal weighed against the possibility of a subtle artifact. It's a high-stakes detective story. A positive, confirmed finding would be the crowning jewel of inflation, solidifying it as the true story. But a persistent, definitive lack of non-Gaussianity, as measurements grow more precise, could be just as revolutionary. It would place severe constraints on inflation, forcing us toward its simplest versions, or it could open the door wide for alternative visions, scenarios like a bouncing universe, where a previous cosmos collapsed and rebounded, or string gas cosmology, where the early universe was a hot, dense gas of fundamental strings. These alternatives can make different predictions about those primordial statistics. The quiet, statistical character of the cosmic microwave background may hold the key. Choosing between entirely different histories of reality, the answer isn't written in large alignments or cold spots. It's in the minuscule, intricate correlations between one whisper of heat and another. The universe's first light may be hiding its most profound secret in the fine print. There's a seventh whisper in the data. It touches the symmetry of reality itself, the Parity Anomaly. Our universe, at its most fundamental level, is supposed to be ambidextrous. The laws of physics shouldn't care about left or right. If you built a perfect mirror of the universe, swapping every left hand for a right, the mirrored version should behave exactly the same. That parity symmetry is a cornerstone, but the cosmic microwave background might be telling us that cornerstone has a tiny, fundamental crack. To see it, you have to look not just at the temperature of that ancient light, but at its polarization. When light scatters like sunlight off the ocean, its waves can become oriented in a particular direction. That's polarization. The primordial light from the cosmic dawn carries its own polarization patterns. They were imprinted when it last scattered off electrons. Scientists sort these patterns into two types, E modes and B modes. E modes have a kind of straight, curling pattern, like the field lines around a magnet. B modes are more swirly, like water going down a drain, and these two patterns have different symmetry properties under a mirror flip. E modes look the same in a mirror. B modes change their handedness. This is where the mystery enters. Some very careful analyses of the polarization data have hinted at a possible, faint correlation between the temperature maps and certain B-mode patterns, a correlation that, if real, would violate parity. It would mean the universe's first light shows a subtle preference for one kind of swirl over its mirror image. A cosmic handedness. The signal is incredibly tentative, buried in noise, hotly debated, but its mere possibility sends a thrill through physics. What could cause the infant cosmos to choose a side? It points to exotic actors on the stage of the very early universe. One candidate is a cosmic string, not a string in the everyday sense, a theoretical, incredibly thin and dense defect in space-time itself. A relic from a phase transition in the universe's first moments. As light passed near such a string, its polarization could be twisted, creating a handed signature. Another, more profound possibility involves a hypothetical particle. The action or action-like fields. These are light, wispy particles, leading candidates for dark matter. They have a unique property. They can make light rotate as it travels, subtly twisting its polarization in a way that prefers one direction over the other. Detecting such a parity-violating signal would be a direct window into physics far beyond the standard model. It would tell us that in its fiery first moments, the universe was not perfectly symmetrical. It had a slight twist, a bias written into the interaction of light and whatever mysterious fields filled the void. This would be a revolution. It means the most fundamental laws governing creation distinguished between left and right from the very beginning. That tiny preference, frozen into the polarization of the first light, could have cascaded through cosmic history, influencing everything from the formation of the largest structures to the very abundance of matter over antimatter. The universe might not be ambidextrous after all. It might be left-handed or right-handed on a cosmological scale, and that ancient light, in its most subtle patterns, might be holding up a mirror to show us which hand it used to write the laws of existence. But there's still a question you have to ask. Are these signals really from the universe, or are they just something from our own equipment? We're not seeing the universe directly. We're looking at maps, and maps are made by something. All that detail comes from satellites like WMAP and Planck. They looked at the sky for years. But they weren't looking into empty space. They were looking through our own galaxy, the Milky Way. It's this bright fog, its dust glows, its gas gives off light. That's foreground contamination. It's a veil you have to see through. Then there's the noise from the instruments themselves, the little quirks in each detector. The huge, complicated process of turning raw numbers into a map. Any step could create an illusion. Scientists know this. They're detectives for distortion. They build detailed models of our galaxy's light and subtract it, piece by piece. They check one instrument against another. They run thousands of simulations to see if a random fluke could look like a cold spot or an axis. Cleaning the signal is its own whole science. And after all that work, the consensus is that the biggest anomalies are still there. They survive the cleaning. They show up in data from different missions. That persistence is what makes them interesting. But the question is never completely settled. Could there be some tiny, unknown effect in the Planck satellite's optics? Some barely their mistake in how we factor in the solar system's motion. The chance, even if it's small, that we're hearing our own machinery instead of the universe, that's taken seriously. That's not a weakness of the science, it's the strength of it. That constant self-questioning, being willing to doubt even the exciting result. That's what makes sure we're really listening. We're not just telling ourselves a story we like. So these anomalies stand there, for now, under a spotlight. They're being checked continuously. They push us to build better instruments, to make cleaner observations, to be more humble with the data. The next telescopes, on the ground and in space, will look at these mysteries with sharper eyes. They'll either confirm these are real features of reality, or show they're just phantoms of how we see things now. Either way, you get to a deeper truth. The first thing we have to see through is this galactic fog. To get to the quiet light of the cosmic microwave background, we have to look past the bright light of our own home. The Milky Way isn't just stars. It's a source of microwave noise, a layered veil. Astronomers call it the foreground, and it's blinding. It's like trying to hear a whisper at a rock concert. The ancient universe is the whisper. Our galaxy is the concert. This foreground isn't one thing. It's a mix of different emissions. There's synchrotron radiation. That's light made when cosmic rays spiral through magnetic fields. These particles are accelerated by supernova, by black holes. It creates a diffuse, crackling glow. Then there's thermal dust emission. Tiny dust grains warmed by starlight, they radiate that energy in the microwave. It paints the sky. You see the structures of dust clouds. And there's free emission that comes from hot, ionized gas. Electrons scatter off ions. It sends out a faint, broad light. It's the signature of stellar nurseries. Of supernova bubbles, these emissions aren't random, they're structured. They trace the spiral arms, they blaze from the galactic center. They form a detailed map. A beautiful map, and it lies right on top of the map we want to see. The Planck satellite had 9 cameras. Each one looked at a different microwave frequency. Because these foregrounds have distinct signatures, they fade or brighten in predictable ways as the frequency changes. The primordial background has its own signature. It's the afterglow of a blackbody, a perfect thermal spectrum, so you use all the frequencies together, like separating ingredients from a stew. This is component separation. You take the data from all 9 channels. Each channel is a mix. The true CMB, synchrotron, dust, free emission, instrument noise. You build a model. You ask, what combination of these components could create the exact pattern we see in every band? The solution that fits gives you your best guess for the CMB. Then you subtract everything else. What's left should be the ancient sky, but theory meets reality. The galactic plane is complex, especially the center. The models for how dust behaves are imperfect. The magnetic fields are tangled, poorly mapped. The subtraction is never perfect. Tiny errors are inevitable. And the terrifying possibility is that these leftover errors could masquerade as cosmic anomalies. Could a mis-subtraction of a dust feature create a fake cold spot? Could the asymmetric shape of our galaxy's emissions, if imperfectly removed, create the illusion of a power asymmetry? The axis of evil could be a ghost in the machine. An echo of our own galaxy's orientation, imprinted during the cleanup. So studying these foregrounds isn't just cleanup. It's a profound field of astrophysics. To trust the whispers from the beginning, we have to become experts in the noisy galaxy we live in now. Every uncertainty in the foreground map casts a shadow of doubt over the primordial anomalies. The cleaner we get the lens, the clearer we see. Whether the flaws are in the universe's first portrait or just in our own imperfect window, even the most careful cleaning can't answer a deeper question. How unlikely does something have to be before we accept it? The cosmic microwave background map isn't a simple picture. It's millions of pixels. Each one is a piece of data. And with a data set that large, statistics itself becomes part of the story. Random chance will always produce patterns that look significant. You'll see faces in the clouds. Our brains are built to find them. In a sky of random noise, you'll always find a cold spot that seems too cold, or an alignment that seems too precise. That's the look elsewhere effect. It's the trap of searching for something unusual across a vast field without first defining what you're looking for. If you search enough data, you are guaranteed to find a 1 in a million fluke. The real challenge is knowing if the fluke you found is the specific 1 in a million event you were looking for, or just the 1 in a million event that was bound to appear somewhere. When a scientist first sees the cold spot and calculates its odds, that calculation is local. It asks, what are the odds of a spot this cold appearing right here? The answer can be startlingly low. But then you have to ask the global question, what are the odds of a spot this cold appearing anywhere in the entire sky map? That probability is always much higher. It's the difference between guessing a single card from a deck and guessing a card after you've looked through the whole deck. The statistical significance of any anomaly shrinks when you account for how much you looked. This recalibration isn't a dismissal. It's a necessary step. It forces a brutal honesty. But some cosmologists argue this perspective can be taken too far. While each anomaly on its own might be explained as a statistical fluke, their collective presence is harder to dismiss. It's not just one strange face in the clouds, it's several, and they seem to be looking in the same direction. The axis of evil, the aligned quadrupole and octopole, the hemispherical asymmetry. They aren't independent quirks scattered randomly. They appear to be correlated. They tell a consistent, if bizarre, story about a universe with a preferred direction and an uneven beginning. The probability of this entire suite of anomalies appearing together in a perfectly standard, featureless universe might be vanishingly small. This is where cosmology meets the cutting edge of probability theory. Scientists are building new statistical tools, new metrics that can test the entire sky for coherence, not just individual features. They run colossal simulations creating millions of fake universes based on our standard model, to see how often such a strange collection of features emerges by pure chance. The early answers are intriguing. They suggest that while any one oddity might be a fluke, the full set of them makes our universe a statistical outlier. A rare bird in the flock of simulated cosmoses, this statistical battleground is quiet but fierce. It's fought with equations and supercomputers, not telescopes. But its outcome will decide everything. Is our universe's baby picture just a random draw from a perfectly normal deck? Or is the deck itself stacked in a way we don't yet understand? The answer lies in the balance between the signal we think we see and the profound, whispering noise of chance in a data set as vast as the sky. That statistical tension leads to a deeper question about what actually drove creation. Cosmic inflation was a major theoretical achievement. It solved real puzzles. The universe is extremely large and smooth. Distant regions have the same temperature, even though they were never in contact. The solution was a period of hyper-expansion. In the first fraction of a second, the universe ballooned by an unimaginable factor. It took quantum fluctuations, tiny subatomic wrinkles, and stretched them across the cosmos. Those stretched wrinkles became the seeds for all structure. Inflation predicts a universe that is isotropic on the largest scales, the same everywhere. It predicts a pattern of fluctuations that should be Gaussian. A perfect, featureless randomness, that's the simplest story. A single field, the inflaton, rolling down a smooth energy hill. But the anomalies we see are like cracks in that sculpture. The axis of evil implies a preferred direction. The hemispherical power asymmetry suggests a lopsided start. These aren't features a simple, smooth roll should produce. It's as if the opening act had a script, but the performance came with an unexpected accent, a tilt. So for inflation, this doesn't mean the theory is wrong. Not necessarily, but it strongly suggests the story is more complex than the simplest version. The anomalies are forcing new chapters, models of anomalous inflation. Maybe there wasn't just one inflaton field but several interacting. That interaction could imprint specific features onto the cosmic microwave background. A slight directional preference, a modulation in power from one hemisphere to another. Or maybe the initial conditions for inflation weren't perfectly uniform. The stage where inflation began might have already had a texture, a slight warp, that inflation amplified but couldn't erase, like blowing up a balloon that already has a faint crease in the rubber. No matter how much you inflate it, that crease might still be visible, stretched across the surface. The most radical interpretation is that standard inflation didn't happen at all. The anomalies could point toward entirely different origins, a bouncing universe emerging from a previous contraction, or a cosmos born from a higher dimensional collision. These aren't mainstream ideas, but the persistent oddities in the data give them a hearing. The true test is in the details. Specific models of complex inflation make specific predictions. They predict certain kinds of non-Gaussianity, certain subtle shapes in the spectrum of the ancient light. The next generation of observatories will search for these precise fingerprints. So the anomalies aren't a death knell for inflation. They are its most rigorous exam. They are pushing the theory to be more detailed, more nuanced, more connected to the actual sky we observe. Either inflation will rise to the challenge, explaining these quirks with a richer narrative, or the data will eventually point decisively elsewhere. The universe's first light is the ultimate judge, and right now, it's asking the theory some very hard questions. The cosmic microwave background has these whispers. Persistent ones, they make you ask, what if the main story isn't right? If simple inflation can't explain the anomalies, then other stories for how the cosmos began deserve a real hearing. These are the alternative cosmologies, not fringe ideas. They're rigorous, mathematically framed possibilities. They paint a very different picture of our origins. Their existence turns the search for anomalies into something deeper, a direct test of which creation story is actually written into the sky. One compelling alternative is the cyclic universe. Imagine a cosmos without a single fiery beginning. Instead, it has this endless, rhythmic dance. A long period of expansion like we see now eventually gives way to a gentle contraction. The universe crunches down, not to a point of infinite density but to a kind of cosmic rebound, a bounce, and from that bounce, a new expansion phase begins. This cycle repeats, potentially forever. In that model, the large-scale anomalies could be echoes, fossils from the previous cycle that survived the bounce. The cold spot might be a remnant of a colossal structure from a prior universe. The missing large-angle correlations could be a natural consequence of a universe that's eternally renewed, not born from nothing. This framework removes the need for a singularity. There's no absolute beginning, just an eternal return. Then there's conformal cyclic cosmology, proposed by Roger Penrose, a Nobel laureate. He suggests a universe where the distant future of one epoch becomes the Big Bang of the next. As a universe expands toward heat death, all matter eventually decays into massless radiation. At that ultimate state, scale becomes meaningless. Penrose proposes that this infinite, featureless future can be mathematically connected to the infinite, featureless beginning of a new universe. The end smoothly becomes the start. He calls each full cycle an eon. In this model, events from a prior eon could leave imprints in the cosmic microwave background of the next. Specifically, the final evaporation of supermassive black holes in a previous universe, through Hawking radiation, could create faint, circular rings of temperature variation in the CMB. Penrose and his collaborators claim to have found evidence of these Hawking points in the Planck data. It's controversial, but the idea is a stunning poetic symmetry. The most destructive objects in one cosmos become the seeds of structure in the next. From string theory comes another challenger, the ekpyrotic universe scenario. In this model, our three-dimensional universe exists on a membrane, a brane, floating in a higher dimensional space. The Big Bang wasn't an explosion from a point. It was a slow, glancing collision between our brane and a parallel one. The energy of that collision flooded our brane, creating the hot, dense state we interpret as the beginning. It's a far more gentle start than a violent singularity. Crucially, an ekpyrotic phase predicts a spectrum of primordial fluctuations that is nearly, but not perfectly, scale invariant. And it can naturally produce a universe that is slightly anisotropic on the largest scales. That could explain the hemispherical power asymmetry. It tells a story where our entire cosmos is the aftermath of a quiet encounter in a hidden, higher dimensional reality. Each of these alternatives makes distinct, testable predictions. They forecast different statistical signatures in the CMB's temperature and polarization patterns. The search for non-Gaussianity, for specific kinds of correlations, becomes a way to distinguish between a universe that inflated, one that bounced, or one born from a collision. The anomalies aren't just puzzles to be explained away anymore. They're potential clues pointing to a specific chapter in a much grander book. This transforms cosmology from a search for parameters within one model into a genuine detective story about the nature of existence itself. The ancient light isn't just a relic. It's a coded message, and we're only now learning there might be several very different keys. That search for a different key brings us to the most staggering possibility. That the flaws in the cosmic microwave background aren't flaws. They could be windows, scratches on the glass of our reality, letting us glimpse something outside. This is the Multiverse Hypothesis. Our entire universe, from the Big Bang to the farthest galaxy, is just one bubble, floating in an infinite, inflating sea of other bubbles, other realities. In eternal inflation, the rapid stretching of space-time never truly stops. It goes on forever. But in some regions, the inflation field decays, it settles. And that settling creates a pocket of stable space. A bubble universe like ours. Each bubble has its own laws, its own constants, its own version of reality. An infinite froth of possibilities. Now the cold spot, that vast, cold region. In a multiverse, it could be a cosmic bruise, a remnant from the distant past of our bubble, when it gently collided with another bubble as both were forming. The energy of that collision, transferred to the fabric of our space, would have left an imprint in the first light. A frozen scar, it's not a void, it's a fingerprint from another reality. Or the large-scale asymmetries, the universe's lopsided power. In a single, isolated universe, that's deeply puzzling. But if our bubble formed within a grander landscape, it might have inherited a gradient. The inflattened field that drove our creation might have had a slight slope across the multiverse. Our bubble nucleated not in a perfectly uniform environment, but on a gentle incline. That initial tilt could have been baked into our cosmic microwave background as a hemispheric difference. The asymmetry isn't an error. It's a signpost pointing to our specific location in a much vaster meta-reality. These ideas are extraordinarily difficult to test. We cannot travel to another bubble universe. We cannot measure the inflattened field outside our own cosmic horizon. But that doesn't make the speculation meaningless. It's a profound shift. Instead of viewing anomalies as problems to be fixed within our single universe, we see them as clues that our universe is not a closed system. The cosmic microwave background, our most precious relic, might be carrying fossil evidence of a reality so grand it defies comprehension. It reframes everything. We are not just cosmologists mapping our own home. We are like explorers in a vast, fog-shrouded archipelago, hearing strange echoes from islands we can never see. The anomalies are those echoes. They hint at shores beyond our own. Whether through a collision scar or an inherited tilt, the first light of our cosmos might contain the faint, blurred signature of our cosmic neighbors. The quest changes. It becomes less about correction and more about connection. The ultimate mystery in the ancient glow may not be about how our universe began, but about what lies just beyond its birth. The universe might have a shape we can't see. The geometry of space could explain the quiet. One elegant idea is cosmic topology. We usually think the universe is infinite and flat. But it could be finite with no edge, a space that wraps around itself like an old video game screen. You walk off one side and appear on the other. The screen is finite, but it has no boundary. It's multiply-connected. On the cosmic scale, our entire observable universe might just be a patch of a larger, repeating structure. The whole cosmos could be shaped like a three-dimensional donut, a torus, or like the surface of a soccer ball, but with more dimensions. These are compact manifolds. In that kind of universe, if you traveled in a perfectly straight line long enough, you wouldn't hit an edge. You'd come back to where you started from the opposite direction. You'd have gone all the way around. Now take that ancient light, the first flash of photons after recombination. In a wrapped, finite universe, those light paths could loop. A photon could come to us directly, or it could have gone the long way around the whole universe and arrived from the opposite side. By the time of that first snapshot, light could have wrapped around space many times. That creates echoes. It means the same primordial structure would show up in multiple places on the cosmic microwave background map. Distant cold spots that seem unrelated might actually be the same cold spot, seen from different cosmic angles. This wrapping and repeating affects the large angle correlations. In an infinite, flat universe, points separated by more than 60 degrees should still be connected. But in a finite, wrapped universe, there's a maximum possible separation. You can't have 2 points farther apart than half the circumference of the whole cosmos. The largest scales are cut off. That would naturally suppress the correlations on the very biggest angles. The quietness we see could be because the universe isn't big enough to hold the grandest waves. The search for this has been direct. Scientists have looked for matched circles in the cosmic microwave background. The idea is, if space wraps around, we'd see the same pattern of hot and cold spots along two perfect circles in opposite parts of the sky. Like seeing your own back in a hall of mirrors. Teams have scoured the data from WMAP and Planck, searching for these paired rings. So far, nothing conclusive. No definitive matched circles, but that doesn't rule it out. The circles might be too large to fit within our observable horizon, or the universe's shape might be more complex than a simple torus. A twist that scrambles the patterns. The possibility stays alive because it solves the puzzle so neatly. It replaces an absence with a geometry. A finite, wrapped universe is complete, self-contained. It needs no edges, no mysterious boundaries, and its shape, written into space itself, could be why the oldest light whispers at the grandest scale. The anomalies might not be errors in the data or flaws in inflation. They might be the first hints that we live in a cosmos that is, in every direction, ultimately finite. There's another possibility: magnetism. We usually think of magnetic fields coming from stars, planets, galaxies. But the seeds for those fields could have been planted at the very beginning. The idea is primordial magnetic fields, vast fields generated not by any star, but by the violent churn of the universe's birth. That existence could change the story of the cosmic microwave background. Those whispers, think of the universe in its first trillionth of a second, a seething plasma, hotter and denser than anything in a star. In that chaos, phase transitions could have happened, shifts in the fundamental forces as everything cooled. Those transitions can create defects, but they can also generate immense electric currents. And those currents could have spawned magnetic fields on a cosmic scale. Fields that stretched across the entire infant universe as it inflated. If they existed, they'd have been frozen into space-time. A background hum of magnetic energy woven in. Such a field would leave a distinct fingerprint on that ancient light. It wouldn't just affect the temperature map. Its clearest signature would be in the polarization. Specifically, it would generate a unique pattern of B modes, those swirly polarization signals. Unlike B modes from gravitational waves from inflation, a primordial magnetic field would create a B mode signal with a different character. A specific spectral shape across frequencies. It would also induce subtle correlations between different points on the sky. It breaks perfect Gaussian statistics. It creates a kind of order, a specific, non-random signature in the data. This is where the anomalies come in. Could a large-scale primordial magnetic field be the hidden architect behind some of the oddities? The hemispherical power asymmetry, that lopsidedness, could arise if the magnetic field itself wasn't perfectly uniform. If it had a gradient, a stronger direction, it could have influenced the plasma unevenly, leaving one half of the sky with slightly more pronounced fluctuations. Even the alignments, like the axis of evil, could be influenced, such a field providing a preferred direction for the evolution of the primordial plasma. Beyond the anomalies, such a field would have been a powerful player in the story of structure. In the Dark Ages, before the first stars, these vast magnetic fields could have provided the earliest scaffolding. They could have guided the collapse of the first hydrogen clouds, channeling flows of gas, influencing the birthplaces of the very first stars and galaxies. The magnetic fields we see in galaxies today, often attributed to dynamos within stars, might have a much older origin. They might be the amplified remnants of these primordial seeds. The search for this is extraordinarily difficult. The signal would be incredibly faint, buried under polarization from interstellar dust in our own galaxy and the signal from gravitational waves. It requires exquisitely precise measurements across many microwave frequencies to separate the components. But the hunt is on. Next generation CMB experiments are being designed with the sensitivity to probe for this specific signature. Finding evidence would be a monumental discovery. It would do more than explain a few statistical quirks in a map. It would open a direct window into physics at energy scales we can never recreate on Earth. It would tell us about the symmetries and phase transitions of the universe in its first second. We'd be witnessing the aftermath of processes that occurred when all the forces of nature were still unified. When the cosmos was an arena for physics we can only theorize about, the silent, magnetic memory of that epoch might still be imprinted on the sky, waiting in the subtle swirls of the universe's oldest light. The story's next chapter is already being written, not in theory, in steel and silicon. To get past whispers, to move toward answers, we need to see that ancient light with a clarity we've never had. And the next generation of experiments is rising to that challenge. These are monumental projects, on the ground and proposed for space, designed to stare at the cosmic microwave background with eyes 1,000 times sharper than before. On the high, dry plateaus of Chile in the Atacama Desert, new observatories are taking shape. The Simons Observatory and the even more ambitious CMB-S4 project. They represent a colossal leap. They'll deploy arrays of tens of thousands of superconducting detectors, working together to map the faint microwave sky. Their goal isn't just a better picture. It's a deeper listening. They will measure the polarization of that ancient light with a sensitivity that was once just a dream. And that precision is the key. It's the key to hunting the most elusive prize, the primordial B-mode polarization signal, that specific swirling pattern in the light's orientation. It's considered the smoking gun of cosmic inflation, a direct imprint of gravitational waves rippling through space-time in that first violent fraction of a second. Finding it would confirm our grandest origin story. But these instruments will do far more than that. They'll generate ultra-high-fidelity maps of the entire sky. Every anomaly gets scrutinized, the cold spot, the axis of evil, all of it under a microscopic cosmic lens. Is the cold spot truly a profound void? Or does it have a subtler structure we've missed? Does the hemispherical asymmetry hold up when we strip away every last trace of galactic interference? The new data will have the statistical power to either elevate these quirks into fundamental discoveries or finally reveal them as artifacts, incredibly complex artifacts of foregrounds and noise. And the maps will be so detailed they'll also serve as the ultimate guide to our own galaxy. By characterizing the Milky Way's synchrotron and dust emissions with unprecedented precision, we can finally clean the lens perfectly. We'll know, with far greater certainty, what is the universe's signal and what is our local fog. Looking beyond Earth, there are proposed space missions, like Light BIRD, designed to escape our atmosphere entirely. From a vantage point in deep space, a satellite like that could survey the whole sky with exquisite stability, free from the atmospheric noise that even the best ground sites have to contend with. It would focus intensely on the large-scale polarization patterns, searching for the faint curl of primordial B modes across the broadest angles. Together, these ground and space efforts are a coordinated assault on the deepest cosmic mysteries. We're on the cusp of a new golden age for CMB cosmology. The coming decade will deliver a flood of data, so rich, so precise, it will force a reckoning. The persistent anomalies will either solidify into new foundations for physics guiding us toward a more complex, more wondrous story of creation, or they will dissolve, resolved by our newfound ability to see clearly. Either outcome is a profound victory for understanding. We are building the instruments that will let the universe's first light speak to us. Not in whispers, but in a clear voice, telling us at last which story is true. But that ancient light isn't the end of the story. Those whispers from the beginning might be talking to the great silences we have now. Our universe today is ruled by two deep mysteries: dark matter, the invisible scaffold holding galaxies together, and dark energy, the force making the cosmos expand faster and faster. These are the rulers of the late universe, and yet their influence, their very nature, might be written into the flaws of that first cosmic snapshot. This is a frontier, The search for one story that connects the universe's birth to its fate. Take dark matter first. We know it's there because of gravity. We see its effects in how galaxies spin, in how light bends around galaxy clusters. Its main job started after that first light was set free. It gave the gravitational wells for normal matter to fall into, seeding the galaxies we see. But what it actually is, we don't know. Is it a sea of undiscovered particles? Could those particles have interacted with the early plasma in a unique way, right before the cosmic microwave background was released? If they did, that interaction could have left a faint signature in the polarization patterns of the CMB. A particular twist or correlation. That's what next-generation telescopes are hunting for. Finding it would change everything. It would mean the oldest light in the sky carries a direct fingerprint of dark matter's identity, from when the universe was only 380,000 years old. Then there's dark energy. This is what's driving the accelerated expansion today. Its effect on the cosmic microwave background is more indirect, but just as deep. It works through something called the integrated Sachs-Wolf effect. Light from the CMB travels through the cosmos, passing in and out of the gravitational wells made by large-scale structures. In a universe without dark energy, the energy lost climbing out of a well is perfectly regained falling into the next one. The net effect is zero. But in a universe with dark energy, the expansion accelerates. The gravitational wells themselves evolve. They become shallower as the light passes through. So the light doesn't get all its energy back. It comes out slightly colder after traveling through an overdense region, and slightly hotter after traveling through a void. That creates specific, large-scale correlations in the CMB temperature map. The exact pattern of those correlations depends completely on the nature and evolution of dark energy. This is where the pieces might connect. Some of the large-scale anomalies in the CMB, like the unexpected quietness at the biggest angles, or the specific pattern of the cold spot. They could be signatures of a dark energy that isn't constant. What if dark energy changes over time? What if it interacted with dark matter in the early universe? A model like that could, in theory, imprint features on the cosmic microwave background that our standard, simple models of these dark components don't predict. Cosmologists are working on these unified models now. They're asking, could one elegant change to our understanding of the dark sector solve puzzles from both the dawn of time and the present day? The ambition here is huge. It tries to weave one continuous story, from the quantum fluctuations stretched by inflation, imprinted as temperature ripples in the CMB, to the gravitational collapse driven by dark matter, all set against the accelerating backdrop of dark energy. The anomalies in the first light might be the early warning signs, hints that the dark forces shaping our cosmos today were already at work, in a different form in its first moments. This research builds a bridge across nearly 14 billion years. It suggests that to understand why the universe looks the way it does now, we have to decipher the subtle flaws in its baby picture. And to understand those flaws, we might need to solve the dark mysteries around us. The quest isn't just about the beginning or the end anymore. It's about finding the single thread that connects them both. These cosmic whispers, they don't really give us a new model. What they give us is a kind of humility. These anomalies in the microwave background, they're not just puzzles. They show how knowledge gets built. They show that our best theories, no matter how elegant, they're not the final word. They're maps. And a map is always an approximation of something more complex. A perfect map of the ancient sky, one that matched every prediction that would have been satisfying. It would have meant we had it all figured out, but it might have been a dead end. These flaws, these inconsistencies, they keep the story alive. They're the open doors. They force a kind of trouble, a necessary trouble. Cosmologists can't just tweak a number now. They're pushed to question the bedrock. Principles like isotropy, the universe being the same in all directions, that's not an assumption to build on anymore. It's a question to be tested. The expectation of perfect randomness becomes a hypothesis, And this questioning, it's not a failure, it's the engine. It drives the creation of new tools to sift meaning from noise. It gives permission to explore radical ideas, cyclic universes, cosmic collisions, ideas that would otherwise seem like fantasy. The process is messy. It's contentious and slow, and that's how understanding deepens. That's the scientific spirit. It's not a triumphant march toward absolute truth, a series of eureka moments. It's a continuous, rigorous dialogue, a conversation between what we predict and what we actually see. The most exciting phrase might not be "we found it." It's often "that's funny." A quiet observation that something in the data doesn't quite fit. That moment of curiosity, that's the starting gun. It prompts the community to look deeper, to build better instruments, to think more creatively. So these anomalies are a gift. They're reminders. The universe is under no obligation to be simple or to conform to our comfort. Our maps will always be refined or redrawn, or sometimes discarded for a new projection entirely. The cosmic microwave background, with its strange alignments and its silent sectors, it teaches us that the journey isn't about arriving at a final answer. It's about learning to ask better questions. And right now, the oldest light in the sky is asking some of the best ones we've ever heard. That necessary trouble found its ultimate instrument in the cold of space. The European Space Agency's Planck satellite. It was a silent sentinel, orbiting a point 1,000,000 miles from Earth. From 2009 to 2013, its detectors did one thing. They listened to the faintest whisper of the cosmos. It wasn't just looking, it was measuring the cosmic microwave background's temperature, its polarization across 9 different frequencies. Building the most precise, all-sky portrait of the ancient universe we've ever seen. This was our chance to see if the whispers were real or just noise in our own machinery. Planck's answer was definitive and deeply paradoxical. The mission delivered a monumental achievement. It measured the key parameters of our universe. Its age, its composition, its rate of expansion, with a precision that felt almost final. The standard model, Lambda CDM, was confirmed, with numbers so sharp they seemed to lock the story in place. The universe is 13.8 billion years old. Ordinary matter, the stuff of stars and planets, makes up just under 5%. Dark matter is about 27%. And dark energy, that mysterious force, fills the remaining 68%. These numbers became the new pillars. Planck had seemingly built the cathedral of modern cosmology on a rock-solid foundation. Yet, in that same exquisite data, the anomalies didn't fade, they hardened. The cold spot was still there, cold and profound. The axis of evil, that strange preferred direction, persisted. With greater statistical significance, the hemispherical power asymmetry was confirmed. Planck's immense power let scientists perform rigorous tests. They ruled out instrumental glitches, data processing errors. The spacecraft's location at that stable Lagrange point, far from Earth's interfering heat and light, gave its data a pristine quality. The puzzles weren't artifacts. They were features of the universe itself. Planck's legacy became this beautiful, frustrating double bind. It gave us our best ever map. A map that validated our core theory and highlighted features the theory cannot explain. The map is flawless, but the territory it depicts has stubborn, inexplicable wrinkles. This duality transformed everything. The mission's public data releases became a treasure trove, the bedrock for thousands of papers. One entire branch of cosmology uses the Planck data to refine the standard model, pinning down the 10th decimal place. Another branch uses that very same data to probe its cracks, testing wilder models against the gold standard. Planck created the modern arena for the anomaly debate. It raised the stakes. Before, you could argue the signals were marginal, maybe from less precise instruments. After Planck, that argument vanished. The anomalies are now permanent landmarks on our most accurate chart. They are part of the data, as real as the cosmic expansion itself. The satellite's final act was one of profound honesty. It didn't solve the mysteries. It handed them to us, clarified and magnified, like a master restorer revealing both the brilliance and the enigmatic cracks in an ancient painting. We are left with a cosmos precisely measured, yet deeply mysterious. Planck gave us the ultimate map of our beginnings, and in doing so, it showed us the story we thought we knew is still being written. In whispers we are only beginning to understand. The search for these cosmic whispers has always been a collective effort. But now, the circle is wider. You don't need a doctorate to contribute to cosmology. The quest to understand the cosmic microwave background has opened its doors. There are projects like Cosmic Microwave Background Anomalies that invite the public to be detectives. They give you access to the same Planck satellite data the professionals use. Anyone with curiosity and a computer can look at these maps of the ancient universe. They can search for patterns, for subtle features an algorithm might have missed. This is citizen science. It leverages a human ability, our talent for pattern recognition. A fresh pair of eyes looking without preconceived notions might spot a connection everyone else has overlooked. The collective scrutiny of thousands of minds becomes a new instrument. This engagement goes beyond direct analysis. The clear communication of these mysteries through documentaries and articles plays a vital role. It demystifies the complex math and physics. It translates the cosmic static into a human story, a story of pursuit. When we share that the universe's baby picture has strange features, we do more than convey information. We highlight the living process of science. It's not a dusty book of settled facts. It's a frontier with unresolved questions and debate. This openness invites everyone to appreciate the journey, to feel the awe that comes from confronting a mystery that spans all of existence. By sharing the puzzle, we acknowledge a truth. Our understanding of the cosmos is a work in progress. The secrets hidden in the first light aren't just for a select few in labs. They're waiting to be pondered, discussed, maybe one day unlocked by curious minds everywhere. This collective wonder, this shared gaze at the oldest map we have, connects us to the grandest story. The story of where we came from and why the universe looks the way it does. And that story, with all its flaws and whispers, is still being written. The first light from the universe doesn't speak one language. To translate it, you need a council. Particle physics joins the story here. The anomalies in the cosmic microwave background, they are messages from a time of unimaginable energy. An energy so high it only existed in the first fractions of a second after the Big Bang. We can't recreate that in any collider on Earth, but we can model it. Particle physicists build frameworks for what might have happened. They propose new fields, new particles, symmetries breaking in that fiery dawn. Each model makes a distinct prediction. It forecasts a specific statistical signature in the patterns of that ancient light, a certain kind of non-Gaussianity, a particular twist in the polarization. The cosmic microwave background becomes the ultimate high-energy experiment, a detector the size of the observable universe, recording the outcome of physics we can only theorize. But that data is a labyrinth. The maps from satellites like Planck contain billions of points. Finding the subtle imprint of a theoretical particle in that ocean is a monumental computational task. This is where data science and advanced statistics converge with cosmology. Scientists develop new machine learning algorithms to sift through the noise. They create techniques to separate the faint cosmic signal from the bright foreground of our galaxy with more precision. They run millions of simulations to understand the meaning of a statistical fluke. Verifying or ruling out a particle physicist's elegant theory often rests on the ingenuity of a programmer or a statistician, crafting a new key to unlock the data. Even pure mathematics plays a role. The shape of space, its possible topology, is a question of geometry. Could the universe be a three-dimensional torus? A vast, multiply-connected manifold? Mathematicians provide the language and the models for these possibilities. They help cosmologists ask if space had this specific, finite shape. What precise pattern would it paint onto the cosmic microwave background? The search for matched circles in the sky is a direct application of topological thinking to an observational puzzle. This convergence is powerful. It shows that a single, profound observation, the detailed pattern of ancient light, can unite distant fields in a common quest. The anomalies aren't just cosmology's problem to solve. They are a beacon, calling out to the frontiers of fundamental physics, to the masters of computation, to the architects of abstract mathematics. The universe's first message is encoded in a cipher that requires all our collective intelligence to break. Each strange alignment, each cold spot, each statistical quirk is a piece of a puzzle that spans the entirety of human knowledge. Solving it demands we listen not with one ear, but with every tool for understanding we have ever built. You need a laboratory, somewhere to run the experiment of creation. That laboratory is in lines of code inside supercomputers. It's the realm of cosmological simulations, a digital universe generator. Scientists write the laws of physics into a program. They start with a set of initial conditions, a recipe for the first moment. Then they press play. The simulation calculates everything: the pull of dark matter, the pressure of normal matter, the push of dark energy across billions of years. It tracks the growth of galaxies. It can trace the journey of the first light, the cosmic microwave background, from its release to a virtual telescope. The output is a synthetic sky map, a pixel-by-pixel mock-up of what the CMB should look like if that theory is true. They don't run this just once. They run it thousands of times. Millions of times. Each run is a slightly different roll of the cosmic dice within the rules. This creates a library of possible universes, a statistical portrait of what a cosmos under those laws typically produces. Now for the test. Scientists take the actual Planck map of our sky. They ask the supercomputers to compare it to this entire library of simulated skies. They look for matches and for mismatches. How often does a simulation based on the standard model produce a cold spot as profound as ours? How frequently does it generate an axis of evil or a hemispherical asymmetry as strong? The supercomputer can give a number, a probability. It might say, in a universe that perfectly follows the Lambda CDM model, you'd expect a cold spot this extreme by random chance in only 1 out of every 10,000 simulated skies. That's a powerful statement. It quantifies the strangeness. This computational work transforms a puzzling observation into a precise statistical tension. It tells us exactly how much of an outlier our universe seems to be. These simulations are also the only way to explore the wilder theories, scenarios with colliding bubble universes, or cosmic strings, or exotic dark matter. The equations for these ideas are often too complex to solve with pen and paper. But you can code their effects into a simulation. You can let a digital universe evolve under those exotic rules and see what kind of CMB map it paints. Then you line that map up against the Planck data. Does the simulated map from a multiverse collision naturally produce a large, cold, circular feature? Does a universe with a certain cosmic topology consistently show suppressed large-angle correlations? The simulation becomes a bridge between abstract theory and concrete observation. It lets us ask, if this wild idea were true, what exactly should we see? And then we can go and look. This digital laboratory is indispensable. It lets us rerun the birth of the cosmos countless times, under countless different sets of rules, searching for the one simulation whose synthetic sky looks in every mysterious detail, just like home. These monuments in the ancient sky, they aren't mistakes. They're invitations, the axis of evil, the cold spot, the quiet halves of the sky. They challenge that elegant simplicity we wanted. They push curiosity to its limit. Each strange feature is a signpost. It points beyond our comfortable map, the standard model. This isn't science failing. This is science, the pure form, a living process. It's driven not by settled answers but by questions, deep, unanswered questions, the investigation itself, this pursuit, this looking for meaning in the whispers. That's what expands our knowledge. Whether these puzzles get solved by the next telescopes, impossibly precise, or by a subtle tweak to inflation, or by some theory we can't even conceive yet. That journey changes us. It deepens our understanding. We look to the future, new instruments, bold ideas, carrying forward that basic human drive, the need to know where we came from. To find our place in the story, that ancient light, that first picture from the dawn of time, it still has stories to tell, and the most thrilling part. The greatest chapters, the ones that rewrite our origin, might be the ones we've only just started to read.